Hello, this is the Unit 3, Lesson 7, Launch, Explore, Discuss. We are building strong roots. We are talking about roots of polynomials today. In the Jumpstart, looking at these expressions, well, actually, they're equations, I hope you see a few patterns. Like, for example, A is an example of a difference of squares. E is a perfect square. How did I know? Well, the terms are perfect squares. A difference of squares is going to have that plus minus pattern when you factor it, and you fill it in with the square roots. A perfect square is going to start with a perfect square. Yep. End with a perfect square. Yep. And the middle will be twice the square root of those. And you fill it in with half the middle term squared. Okay, B is not a pattern. That actually is going to give you imaginary solutions. I hope you remember that I is the imaginary unit. And you can have things that cannot be factored that can only be solved with the quadratic formula or completing the square. And I think D is going to be one of those ones that is going to have you're only going to be able to solve it with quadratic formula. And then C should be able to factor that. But let's move on. We're going to talk about something called the fundamental theorem of algebra. Okay, fundamental theorem of algebra was introduced in Integrated 2. And here's a short statement of it. It's not the official statement, but it's sort of the gist of it. An nth degree polynomial function has n roots. What that means is whatever your exponent is that's the highest, that's basically how many answers to an equation you're going to have. So we're going back to quadratics again to see if we understand what's going on. So number one, the roots, since they gave us the graph, we can just identify them. They are here at -3 and here at positive 2. So -3, positive 2, and they are real roots. Then, on part B, yeah, there's 2 roots, but they're not whole numbers. So we could use the quadratic formula, which we're not going to talk about just yet. And that will give us 2 roots. They're still real. And just to give it to you, it's 1 plus or minus 2 root 2. On C, there's only 1 root. But you notice how it's bouncing off the x-axis? We call that a root that has multiplicity. In fact, although it's real, there's only 1 real. Actually, I put the wrong thing here. It's not 1. It's at x equals 2. There's 1 real root with a multiplicity of 2. That means it's repeated. A repeated root. So look for those bouncers. D, Doesn't have anything. Oh no. Well, guess what? The roots are imaginary, or we would say complex. And again, using quadratic formula, we could come up with 2 plus or minus I. Type of roots, complex. Remember, complex means a real part with an imaginary. Real with imaginary. The real part would be 2. The imaginary part would be I. Number 2, did all the quadratic functions have 2 roots as predicted by the fundamental theorem of algebra? Yes, but you have to count multiplicities for twice. So that would be, let's see which one did that. That would be C. Multiplicity in part C. And by the way, if we factored this, this would be x minus 2 squared. So that squaring of a root is what led to that happening. Number 3, it's always important to keep what you previously learned in your mathematical bag of tricks so that you can pull it out when you need it. What strategies did you use to find the roots of the quadratic equations? Well, I hinted at what they could have been. They could have been quadratic formula. You could have had just factoring and then completing the square. Which, of course, we'll have to review a bit in class. So here's something to think about. It says, using your work from problem 1, write each of the equations, quadratic equations, in factored form. When you finish, check your answers by graphing, and when possible, and make any corrections necessary. So this first one would be multiplies to -6, adds to 1. That could be 3 and 2, where the 2 is the negative. So the factored form of f of x would be x plus 3, x minus 2. And they want to know about the roots. No. Well, one thing to notice is that the roots are the opposite of what the factors are. So if you look back up here on number 1, the roots were at -3 and 2, right there, but the factors are +3 and -2. That's not a coincidence. That's going to happen. Okay, how'd they get the factored form for this one? Well, got to use the quadratic formula, I think. Or we can complete the square. Let's use the quadratic formula. So if this was equal to 0, which is where you're going to have a root, then x equals -b. Remember, this is b, this is a is 1, and this is c. So x equals -b plus or minus the square root of b squared minus 4ac all over 2a. So it's 2 plus or minus the square root of 4 plus, and then 4 times 7 would be 28. And that's over 2. So 2 plus or minus the square root of 32 over 2. What is the square root of 32? Well, that's 16 times 2. Or the square root of 16 times the square root of 2, it's 4 root 2. So this is 2 plus or minus 4 root 2 over 2. And now I can reduce. 2 goes into 2 once, 2 goes into 2 once, 2 goes into 4 twice. And this is 1 plus or minus 2 root 2. Okay, we still haven't written it in factored form yet. So here's one way to write it in factored form. So g of x could be written as x minus 1 plus 2 root 2 and x minus 1 minus 2 root 2. Why is there a minus sign there? Well, because if x is equaling 1 plus 2 root 2, and we subtract this entire thing to make it equal to 0, well, here's the entire thing subtracted and equal to 0. Why 0? Because that's where a root is. A root is a number that makes an equation equal to 0. See, we already did that one. That one is a perfect square. And what about D? And that's in factored form. Well, let's complete the square on this one. X squared minus 4x, and you take the number 5 and you move it to the other side. Then you need to add a number here that's going to complete or finish the square. Now here's how to do it. It's half of b squared. So if b is negative 4, half of negative 4 is negative 2. Negative 2 squared is 4. I'm going to add in a 4. But I can't just add in a 4 on the left side. I'm going to add in a 4 on the right side to balance it out. So this is x minus 2 squared equaling negative 1. Now I take the square root of both sides. That was the whole plan, was to make a perfect square. So x minus 2 equals plus or minus. Now the square root of negative 1, that's the imaginary unit. That's I. Okay, so x is going to equal to, and you add the 2 to both sides, 2 plus or minus I. Now, factored form is we're going to write that with subtractions. K of x is x minus 2 plus I, and x minus 2 minus I. Some of these look god-awful, don't they? Terrible. Based on your working problem, 1, would you say that roots are the same as x-intercepts? Close. They can be the same thing. So a root is a number that when input causes the function to equal 0. So in other words, f of x equals 0. But, and that sounds like that's going to make an intercept, right? But complex roots are not on the x-axis. Because the x-axis is for real numbers only. Based on your work in problem 4, what's the relationship between roots and factors? Okay, so if you get a solution, if x equals a and a is a root, then x minus a is a factor. Remember, factors are things we multiply with. Next page. Now let's look closer at a cubic. We've worked with transformations, but this is not transformed. Okay, if we look closely at the roots, it says use the graph to find the roots. Here's one at about negative, what would you say, 3? Or negative 2? Yeah, negative 2. Here's one at 0. And here's one at 5. Use the equation to verify that you're correct. Show how you verified each root. Okay, so if the roots are negative 2, 0, and 5, that means when I use division, I should be able to get a 0 remainder. So if I use negative 2 and I go 1, negative 3, negative 10, and 0, I get 1, negative 2, negative 5, 10, 0, 0. If I use 5 with 1, negative 3, negative 10, and 0, I get 1, 2, 0, 0. What about 0 itself? Well, obviously, if you get g of 0, then that's going to be 0. 0 cubed minus 3 times 0 squared minus 10 times 0 is 0. So all three numbers, remember, the remainder under synthetic division, or the remainder when you have one of these simple factors, the remainder is the function value. So they are all zeros. They are all roots. Number 8, write g of x in factored form. Okay, factored form of that would be, okay, remember, so in the factors, it's the opposite of what you're going to see for solutions. And you're going to have an x for 0. So that's 0. That's for negative 2. And this is for positive 5. Now, how can I verify that that's true? Well, if I multiply it back together, I should get the original. If I multiply this, I'm going to get x squared plus 2x. And then let's see, if we do a little box here, and we do x minus 5 and x squared plus 2x, we're going to get x cubed minus 5x squared, 2x squared, and negative 10. And if you take that out of the box and combine like terms, you are going to get, I missed an X right here, you are going to get what we had right here. So it works. Are your results in problem 7 consistent with the fundamental theorem of algebra? Yeah, fundamental theorem said if you have the third degree, if you have a cubic, then you should be expecting 3 solutions. As long as I account for multiplicity. Cubics should have 3 solutions or roots or zeros, sometimes we call them. Here's another example of a cubic. Use the graph to find the roots. Okay, here's a root right here, -4. And here's a root over here at +1. So -4, but that's bouncing. See, so that has to have a multiplicity of 2. And then +1. So if you add up a multiplicity of 2, so there's double root on -4, and then another one at 1, that does add up to 3. It's as simple as that. Number 11, write f of x in factored form. Okay, verify it works. So I have f of x equals, so if -4 is the root, +4 is the factor, that's squared, there's your multiplicity, and then you have x minus 1. Can I verify that that's x cubed plus 7x squared plus 8x minus 16? Okay, sure we can. We can multiply out x plus 4 squared. That's a perfect square. So that has a nice little pattern. And then if we take that and we multiply that by x minus 1 with x squared, 8x, and 16, we get x cubed, 8x squared, 16x, negative x squared, negative 8x, and negative 16. So x cubed plus 7x squared plus 8x minus 16. Is that what we got before? That is exactly what we got before. So it works. Number 12. Are the results you found in problem 10 consistent with the fundamental theorem of algebra? Yes, as long as we count the root at -4, let's take off parentheses, -4 twice. Then you got -4, and what was the other one? 1. 13. We've seen the most basic cubic polynomial function, h of x equals x to the third power, and we know its graph looks like this. Explain how this is consistent with the fundamental theorem of algebra. Well, that means that 0, the number 0, is a triple root. In other words, it has multiplicity of 3. Here's one more. You'll notice that it's given to you in factored form. Use the equation and the graph to find the roots. Okay, so here's one root. X equals -3. But this other one, x squared plus 4, if that was going to equal 0, then x squared would equal -4, and that would mean x would be plus or minus 2i. Ah, see, they're imaginary. And then it adds up to 3, doesn't it? Use the equation to verify each root and to show your work. Well, probably the easiest way to do this is to substitute. If you did this, you're going to get 0 times negative 3 squared would be 9 plus 4, and that's just 0. If you did p of 2i, you would get 2i plus 3 times 2i squared plus 4, and that will equal to 0. Trust me on that, and negative 2i will do exactly the same thing, and you'll just have to trust me on that one as well. Just a bunch of algebra, arithmetic, to get that to work. Are the results you found in problem 14 consistent with the fundamental theorem of algebra? Yes, because 1 real plus 2 imaginary equals 3, and that's what we get when we say cubic. 3 roots, third degree. 17. Explain how to find the factored form of a polynomial given the roots. There's the bell. We're running out of time. You're going to have to do, like, if the A, B, and C are the roots, then it's going to look like A and B and C. They're all x minus whatever. And explain how to find the roots of a polynomial given the factored form. To find the roots, set each factor equal to 0 and solve. And that's what I did up here when I found these 2 roots right here. I set the factor equal to 0 and I solved it. Whew, that was a lot of stuff, wasn't it? That's a lot to take in, but hopefully you've had time to digest it, and we'll see you next time.